Hey team, Thrasher here. We're kind of taking a pause in the physics information to look at a skill, a very important skill that comes into play both in labs that you'll do in your college level class, but also on the AP exam if that's what you're after. It's known as linearizing graphs, or sometimes it's called linearizing data, or just linearization, all very similar sounding. Depending on what source you're looking at, you might see it written one way or another. Okay? Now, to be honest, before I get into what that is and why we do it, I have a quick aside, almost, okay? I have a quick little prologue. I want to chat briefly about this idea about slope, okay? Remember, if we have a straight line, way back from algebra class, you learned this slope-intercept form. I know technically it's like y equals mx plus b, and technically there are times when this b, this y-intercept is valuable, but admittedly, we're going to kind of ignore it for this video. So I haven't forgotten about it, but our focus isn't on this intercept. So that's why you're going to see me just writing this part. It's like when there's not a y-intercept, okay? So we know y equals mx. What does m represent? Well, if you remember from algebra class, or you just look at my screen, that's the slope of the line. That represents the slope. If you graph y, technically what? That's your dependent variable. You're never going to hear me worry or really use those terms in class. Not super important here, okay? But the y values, your x values here, the slope is represented by m. It's this thing that's being multiplied. So real quick, if I was to graph the line, just going back to algebra class, y equals 16 times x. I wanted that graphed. It would look like some line. What would the slope be? Well, the slope would, of course, be 16. The slope being that rise over run, that would be equal to 16 because, again, it's that thing that's kind of right in front. It's that coefficient in front of x. What if, however, I wrote it like this? I want you to graph the line y is equal to 8 times 2x. Graph that line. Well, if you're thinking, wait a minute, Thrasher, that would be the exact same looking line. Ah, you'd be right. What is the slope of this line? Oh, well, the slope, just like here, the slope was equal to 16. Here, the slope is, well, it's 16. It's 8 times 2. I could write it out this way. It's still the thing that's being multiplied by x, the thing that's being graphed on the horizontal axis. What if now I ask, what is the graph if I have y is equal to the square root of 256 times x? It's again the same thing. The slope is root 256. That is 16. Or what if I did this? Y is equal to b times x, where, I don't know, b is not a variable. Okay, b is just a number. B is equal to 16. Well, that works too. The slope is b. Team, this is what I'm getting at, okay? The main idea. While you maybe haven't thought about it in this regard before, in a graph, when we're making these lines, I'm going to move my head up. There I go. Okay. The slope is whatever the coefficient is that's being multiplied by x. That's being multiplied by, again, technically it's what? Your independent variable? Not important. Okay. Being multiplied by that horizontal thing. Keep that in mind as we continue on for the next set of slides, okay? Okay, well, here we go. Linearizing data. What does that mean? It's when you have a graph that is not a straight line. So here's just a curving graph, right? Or maybe it's when you do a lab and you make data points on a graph and you're not obviously getting a straight line, but if you were to draw the trend, it would be some curve. Linearizing data, linearizing a graph, is when you take that graph that looks like this and instead you turn it into something like this. The point is, well, team, it's tough to analyze a graph like this, especially in a class like AP Physics, where we're not using calculus and we're not spending a lot of time like punching in plots into calculators or graphing programs to do deeper analysis. If I just wanted to do analysis by sight or real quick pencil on paper scratch work, we know how to do that for lines. We know that point slope equation, y equals mx plus b. We know, oh man, we just learned in past videos that the slope can be representative of important information. So if we have graphs that are a little more complicated, this, I don't know, maybe it looks like a quadratic graph. If we can turn them into a linear graph, well, it's easier to analyze. And often that means looking at the slope, which is easy to do, okay? So, okay, what exactly does that mean? Before I get into the why, I'm actually just going to explain how we go about linearizing. And it's right up here. How do we linearize? What it is you just plot what the actual function is on the horizontal axis. That's a weird thing that I'm saying right there. So what do I mean? Let's say this is my graph, okay? So again, not perfect, but let's say I have this y equals ax squared. A is just, some number. It's a curving line. This is part of a quadratic equation, all right? Kind of complicated, tough to analyze. We're certainly not going to do like the quadratic equation here. Oh yeah, please spare me. If instead of graphing y and x, which is of course what you're all used to doing, right? That's what algebra and geometry, man, that's what you've spent your whole math career doing for the most part. If instead of graphing y and x, what if on the x-axis I graphed x squared? If you're thinking to yourself, Thrasher, you can't put x squared on the horizontal axis. Well, why not? What rule is there that says I have to just put y and x there? If, in fact, I graphed or I plotted x squared on that horizontal axis, notice what we have. Here's that original version of our slope equation, okay? Y equals mx, where the coefficient is that slope, the thing right in front of x. Look at the translation I've done. Well, that's still the same here, okay? The thing that's on the horizontal axis, which now just happens to be x squared, well, now whatever coefficient there might be, now that's the slope of the line. And if you do this, if you take the x squared and that's what you do to the data, you will actually get a straight line. Don't believe me? Let's try it. So here's my data table. You could hit pause if you wanted to, okay? But these values here are what's happening if I'm using my y equals x squared. So when x is 0 or when x is 1, y squared is 1. When x is 2, x squared, that makes it 4. So this here and this here, that gives me this graph. But let's just say for funsies, I decided to take these x-axis data points and I just squared them. Because this is America, I can do what I want. So now I'm just going to square it. So of course, 1 squared is still 1. 2 squared is 4. Oh, notice, 4 and 4. 3 squared, because I'm choosing to square it, is 9. 9 and 9. 16 and 16. I have the exact same spots on the y and x axes. I get a straight line graph. Weird. You may have never seen this before, okay? It doesn't just have to be x squared. No matter what your function is. And on this graph that I admit I stole from the internet, they're using examples of physics concepts. They have force and time. Some of these equations kind of make sense. Some are maybe a little bit made up, or at least they're not obvious. But maybe focus right here. For a linear line, the work's already done. But again, if I put the x squared for a y equals x squared graph, I end up with a straight line. Here is an inverse graph. Normally, when you plot y and x, you get some inverse looking like this. But imagine if just for funsies, I took my data and I took the inverse of it. And I plotted that. I would again get a straight line. Here is, oh man, an inverse that's being raised to a power in that denominator. But again, if I chose to do that on that x-axis, what I'd be left with is a straight line. Weird. Now, ultimately, maybe you're thinking to yourself, Thrasher, why? What's the point of this? Here is why. This is a physics class. That means we're doing labs, and we're trying to use data to analyze or apply an equation to learn something. For example, okay, we haven't quite covered this, but there's an equation for things that are falling. What the equation says is that the height things fall at, how far they fall, well, that's equal to 1/2 times g. G has to do with how quickly things accelerate because of gravity. We haven't really gone over it yet. Multiplied by the time squared, okay? This is a known physics equation. Well, we could do a lab here in my classroom where students drop things from certain heights and they measure the time to fall. Now, if you did that, because the relationship is t squared, you would get a graph like this. But if we chose to linearize, to take what's happening to that x-axis, time in this case, if we chose to square it, so it's almost just like making another column in your data table and just going back with your calculator and squaring all those times. Well, if you graphed t squared, you would get a straight line. And then what could you do? You could draw a line of best fit, and you could find the slope of that line. Team, this is a little tough, okay? Remember, normally it's that coefficient that gives you the slope. if I was graphing t squared here, what would the slope of this line, which you could measure, right? If we had actual numbers, you could do rise over run, maybe you get a value. What would the slope be equal to knowing this relationship? This is a little tough, and it goes back to my little prologue. It's always that thing that's being multiplied by what you're plopping down on that x-axis. So let's say, I'm just making up a number. This doesn't make any real sense. But let's say we found the slope is equal to 5. Well, bam, team, that slope is this right here. 5 is equal to 1/2 g. And notice, you could find g, the acceleration in this example. And then you could send astronauts to Mars, and they could do the same silly little experiment, graph things, because, oh man, they left their graphing calculators on Earth. They could find the slope, but they could figure out what the acceleration is on Mars, or on Jupiter, or wherever you're doing it. So this idea of linearizing, by changing what we put on this x-axis, helps us get a straight line, and then finding the slope can give us valuable information. And team, if you're unsure, like, is this just Thrasher being weird? No. College Board has questions where they will ask you on their free response, like, what should you graph so the slope gives you speed? I don't know, okay? So this idea, it doesn't show up super often, but sometimes you'll be asked to linearize. And we're going to be doing a lab team where linearizing is going to help us more easily understand what's going on, okay? So this is weird, but there's a method for this. It helps us more quickly understand what's happening. I have one quick last point, as this video is getting a little long, okay? 12 minutes. Oh, let's wrap it up. Okay, one last thing. When we're in our physics class, if I ask you to graph data, okay, you might be familiar, you might have been asked in past science classes to draw a line of best fit. What that means is maybe we were measuring the position of a ball at different times as we were rolling it down the table. I don't know. And all these blue dots, all of these are data points. Of course, they're sources of error, right? Maybe you mistimed it. Maybe someone bumped into the table. So your data is not perfect, right? The way we can help reduce the noise, how to reduce and get a general average, is by drawing a line of best fit, where you have a straight line that's kind of intercepting your data. About half the points are above, half the points are below. Here's what students mess up. Most of them remember how to do a line of best fit if you didn't know before. But because I just talked about how finding the slope is important, if you are finding the slope of a line of best fit, or I ask you to make a graph of your data and you're going to find the slope, you're choosing 2 points on the line. Okay, that is crucial information. What do I mean? You don't choose 2 of your data points. That is a science sin. The whole reason we're drawing a line is because this line represents an average. It helps us reduce that noise. So you don't choose your data points. This point is not particularly special. In fact, maybe this was when someone bumped into the table. We don't want that. We want 2 points on the line. Now, you can make your life easy, like, ooh, this would be a nice easy one. So maybe you choose this spot, and I don't know, maybe this spot. But you're not choosing your data points. The data points are what you use to then draw an average. And if you're finding the slope of that line of best fit, you're choosing 2 points on the line. You're going to lose points on certain labs if you're choosing data points. Even if, oh man, I know you want to do this. If you're like, well, Thrasher, look how close that data point is. Can't I use that one? Oh, you're getting onto a slippery slope. For the most part, teachers want you to choose 2 totally different lines. At least that's not as bad a sin as if you chose like this point here. But you should get used to drawing a line, choosing 2 points on the line, and then of course we're doing that rise over run. That's what I mean, right? Rise divided by run. That's how you do your slope. y2 minus y1, 1 divided by x2 minus x1. Okay. But linearizing, it's weird, and you may not have seen this before, but it's a way to get straight lines from otherwise non-straight relationships, and it makes it easy to analyze using the slope. Okay, thanks a lot for watching. I'm out.